Edge shaping, this was also a project that we did at Infineon. It was mainly from power electronic devices, and as already mentioned, it's about shaping the edges of our signal transition. And we were also interested in how much reduction we could get when we are shaping these edges from such a signal. And in the same way as I've drawn it here, we made some calculations. So this is our typical switching signal. It's a 100 Hertz switching signal, switching in current of 5 amps. And yeah, we could transfer this time domain switching signal into the frequency domain with a certain measurement technique that is behind this. Measurement technique related to the measurement of the conducted electromagnetic emission. And this was then the frequency response in the frequency domain. And here in the background, you can see some limits. They are defined by, in this case, the CISPA 25 standard, which says that the electromagnetic emission of such a chip should be below the limit. And the limit class, is difficult to see, is, for example, here. So we are violating this specification by, I don't know, more than 40 dB. So the next step was to limit the electromagnetic emission in the frequency range to be below these limits. So we know how the signal in the frequency domain should look like. And what we did now was transferring the signal from the frequency domain back into the time domain to check how such a signal should look like in the time domain that in the frequency domain is below the limits. And interestingly, the signal then finally looked like this. And now it was the challenge for the IC designers to design such kind of output drivers that are producing a signal that looks like this. Okay, not that super easy, but what we could see is that in comparison to this signal, there is a certain smoothing function. So the edges should be as rounded as possible. And this was then finally designed. So this is the conventional gate driver. So we have a big power, in this case DMOS switch, and usually the DMOS switch is turned on and turned off by an N-channel transistor or by a P-channel transistor. And in such kind of current mirror topology, we have a current source, and the current here is mirrored to this branch, and here again mirrored to this branch. And depending if I'm turning on the N-channel transistor, I'm discharging the gate in order to close the switch, or if I'm turning on this switch here, I'm forcing the current over the P-channel transistor to charge up the gate in order to turn this DMOS switch on. And in this edge shaping topology, we also made some feedback circuitry. So we were measuring how far is this output signal already increased, and based on how far it is increased, we have then changed somehow this current here by changing the current source. And by changing the current source, we could really smooth the edges of our signal transition from such a sharp edge to a really rounded up edge. Yeah. And then we were interested how much reduction in the electromagnetic emission we could get. And as you can see here in this lower frequency range, the red characteristic is the one without this slew rate controlled, or without this edge shaping circuitry, and the green one was then the one with the edge shaping circuitry. And in the lower frequency range, this was up to 25 dB, which is pretty much. Yeah, we already have discussed this frequency contribution. This was the internal switching frequency of the charge pump, which was not changed. So therefore, there is not a big difference between the green and the red curve here. Okay, but the interesting thing is, especially in the lower frequency range, we have a quite significant reduction with a very, very simple circuitry. Just a feedback loop with an operational amplifier, and the current source is driven. So this doesn't cost that much. But on the printed circuit board level, if you have to reduce in this frequency range the emission by 25 dB, here we are in the kilohertz range, this means heavy filtering. So you really need big inductances and big capacitances. And this is definitely more expensive than providing some know-how into the chip design.